My name is Clemens Fastas. I'm the technical lead on the .NET Service Bus, which means that I'm a program manager part-time, and I'm a dev part-time, which means that I get to define features, and unless some of my elders don't object, I get to code them too, which is kind of fun. And of course, I'm not doing that myself. I have a very capable team who are doing, of course, most of the work. And we're really glad that we can show you the things that we've done so far. So I'm going to be talking about the Microsoft .NET Service Bus, part of the Azure Services Platform. And that's a project that we are now doing in, we've actually done a few releases already. We had a small circle of friends who followed us because we were hiding behind a code name that didn't make very many people very excited about what we were doing, and frankly got some people confused. So it was called BizTalk Services. And since the last public release of BizTalk Services, a lot of things have happened. And I lost a lot of sleep. So let's go. So the Windows Azure platform is basically the underlying fabric that runs all of our stuff. Where I'm going to talk tomorrow a little bit more about how we scale and how our backend systems work. And all of those things will eventually run on the Windows Azure platform proper. We have a lot of building block services, pieces that you can use for your applications. And the important thing here is we don't make you run all the things in the cloud. This platform is as much about componentization of capabilities as it is about really a cloud OS where you basically run everything on. The .NET Service Bus in particular and the Access Control Service are services that allow you to attach services that you run on premise into the cloud and make them interoperate not only with cloud services, but also amongst each other. One thing that we do with the .NET Services platform is we enable you to reach into more devices, into more machines. If you're running an interactive application, and that interactive application sits on someone's notebook, and that someone sits in a hotel lobby, somewhere behind an unknown wireless LAN, and you want to push notifications or want to push something to that machine, that's hard. I mean, how do you find it? If you're building a consumer application that tries to just do photo sharing, that's hard. So I'm going to talk about the .NET Services Service Bus that enables those features. So first I'm going to talk about what a service bus is. Then I'm going to talk about a little more detail about the connectivity challenges. And then I'm going into the feature areas, naming the service registry and messaging. And messaging will be the largest portion of what I'm going to be talking about. We all by now, at least from architecture, sometimes from architecture, know what an enterprise service bus is. An enterprise service bus takes all of our application that we run in the enterprise, point of sale, supply chain, CRM systems, our database backend storage, takes all of those systems and integrates them into a common fabric. The enterprise service bus very often is Ethernet with appended services. So really we have a fabric inside of our enterprise which is based on Ethernet, based on TCP/IP, and then we're running server systems that help knitting all those things together into a common fabric. So we have federated identity and access control, and that's provided mostly in many enterprises by Active Directory or other identity and access control systems. We have naming and service registries, while naming and service registries for services may be provided by Active Directory, may be provided by UDDI services, may be provided by something that you just build yourself. And then there's a messaging fabric, and the messaging fabric really foots on TCP/IP, and there's several components in your architectures spread across the enterprise which give you different messaging capabilities. You will have queuing systems, you have systems like BizTalk, which have a hub and spoke model, or you just do a peer-to-peer messaging using technologies like WCF or Sun Microsystems Metro Stack for web services, or you're basically just building a REST network mostly based on HTTP-based web services. So you have a messaging fabric that you're running. But it's a pattern that has developed, and it's a pattern that we use in the enterprise. So we took that pattern and said, let's build all those components in a similar fashion for internet scope, so that you can take your ISB, you can take your enterprise service bus and selectively expose endpoints for higher reach. Because your enterprise service bus, understandably, is mostly shielded from outsiders using your own firewalls and your own protection mechanisms, and it's really protecting the data you have in the enterprise. But there's endpoints you want to expose. There's also satellite applications that you want to have access to into the corporate network, not necessarily with exposing services directly through ports on your own firewalls. You want to make that more secure. If you want to have internet scale connectivity, it would be a good idea to have an internet scale demilitarized zone that can help you create that connectivity, and to establish bidirectional connectivity as well. Because if you look at the development of internet applications apart from the web, you see that many applications are taking a huge bet on bidirectional connectivity. Over 50% of internet traffic, for good or bad, is done through BitTorrent. Big, huge bet on bidirectional connectivity. It's the biggest application on the web. It's more than HTTP. Skype, Messenger, Yahoo Messenger, all those collaboration applications, huge bet on bidirectional connectivity. Bidirectional connectivity is really hard. Why is it hard? IPv4 addresses are out. There's no threat of them being out. They're out. We're done. Dynamic IP addresses are allocated by every ISP. If you want to have a static IP, you're paying for it. With many ISPs, especially in developing countries, they're natting you. You don't get a public IP anymore. We're done. How does BitTorrent, I'm taking that as an example because I'm just guessing that some of you use it to share private photos. Do you know that BitTorrent isn't working? If you don't have a public IP address, you don't play. So network address translation is a thing. The internet is owned by the bad guys, which means we have firewalls on our machines and the corporate perimeter, and there's a firewall basically in every step of the way. And that's causing issues for applications that want to do something good instead of something bad. So we have a machine firewall, we have a network firewall, we have network address translation, and we have dynamic IPs. How do you create bidirectional connectivity in that case? It's really hard. So how do people deal with that thing? Well, they have dynamic DNS, which sort of works sometimes. And then you got to have an open DNS system, dynamic DNS system that you can really rely on. They use NAT port mappings on their firewalls to particular machines, which means you're opening up a hole in the firewall, and even worse, you're punching a hole straight to a machine. Or they use UPnP. UPnP is a wonderful technology. On my, you're not having a phone call in my talk, have you? UPnP is a wonderful technology. On my personal home firewalls, I have it turned off. And I know why. Turn it off. It's kind of, you got to think about how the security system works. Anyways, or they just open inbound firewall ports. All of those things are brittle or difficult or potentially insecure, and they open up your system for all sorts of attacks. Opening a port on a firewall is a dangerous thing if you're not 100% sure that that application is actually hardened against all possible attacks. So it's a problem. It's a problem that we deal with by taking risks right now. who needs bidirectional connectivity? Who needs to have a way to talk to an endpoint that's sitting somewhere out on the internet? Practically every interesting app that is not a web app. Practically any app that's not hosted somewhere in some hosting facility and responds to web requests. If you want to do peer-to-peer connectivity, if you want to enable the mobile workforce with more than just HTTP and HTTP polling, you need this. So with that, we come to the service bus. The service bus gives us those capabilities that we're missing. So let's start with dynamic IP and dynamic DNS. We need to have a way to go and name services. And when I mean services, I mean an entity that responds to messages and can send messages back. How do we name those things? Now, is there anything broken with DNS, really? No, DNS is actually working pretty well. But it has some practical constraints. First of all, there's a high update propagation latency. If you want to update DNS, updates are not instant. Well, in theory, they really are. If you use a dynamic DNS system, you set the TTLs to 0. But many applications basically just go and do a name resolution and then stick with it. And so you basically have to shut them down and open them up again. That's a practical constraint that just is embedded in the apps, not necessarily the system. There's increasing pollution by ISPs, so-called DNS assistants. You type in the wrong URL, you get a wonderful page, and they say, oh, you mistyped your URL. Were you searching for something? Here's some ads, and here's a set of results. That's breaking DNS. DNS names hosts, not services. If you're hosting 500 services in a corporate system, you name them all with one DNS name. And there's a limited write access model. Like, how do you actually update dynamic DNS? That's a thing that's custom in most cases. So the service bus naming system is a naming system that's DNS integrated. So we use the root of the names of the DNS system, but then we have our own naming system that's sort of extending this, which is hosted in our cloud. And this is sort of how this works. We have a structure, we have a hierarchy of names that's maintained by our system. So we have a federated namespace model. The root is rooted in some DNS name, servicebus.windows.net/services for this CTP. And then we have a federated name structure, which you can structure as you like. And you can put names there, which means description of services, external references to services. So this is sort of like UDDI, or sort of like LDAP, or, and we're constraining that to service references very strictly, or you can put listeners into those places so that people can actually send messages to you through that naming tree. And I'm going to show you that a little later. So for the PDC CTP, the November CTP, the naming structure looks like this. It's servicebus.windows.net/services/your solution account that you get to create once you have one of those activation codes. And then /name, and that's a hierarchy, that's a tree that's completely up to you how you want to structure that. And this is where you can go and start listening or start registering services. After the PDC, in one of the next milestones, and milestones for us is about roughly a quarter, we're going to switch that structure over, and it's going to be solution.servicebus.windows.net/name. And we might, and that's a might, and therefore it's not on the slide, is allow you to grow that name, that URI, that projection, to both sides. So you may do name 2, name 1, solution.servicebus.windows.net/ and just create a root there, or grow it out to the other side, as you wish. Because we're all projecting this into the hierarchical naming structure that we have at the back. But this is a naming system that's focused on services and not focused on hosts. So it's completely separate from the notion of what machine that runs on. Servicebus.windows.net is basically just a resolution into our naming fabric that we have, but your names, your endpoints can live somewhere completely different. There's no direct API for the naming system per se, but there's two entry points to it. One of them is the service registry, and one of them is the messaging capabilities per se. So let's talk about the service registry first. The service registry is a registry for service endpoints. It's representing itself as an Atom feed. You can access it, you can modify it using Atom pub or by creating listeners. It's a registry, a service registry that's layered over the naming system, so it's one API for it. The other API that we have for it is our listener system. So we have a Atom 1.0 feed hierarchy, and we have WS transfer support for pushing endpoints as well. Before I show you something, so on your solution, if you hit that endpoint of your solution, you will find a feed, and you can then start pushing things into that feed. So basically by opening listeners or just pushing data into it. And there comes the demo. Interesting. That should be on D. When I wiggle this, is something moving? Yes. So I have a little solution, and what that little solution does is it creates a bunch of endpoints. So let's try and do that. Oh, let's show the feed first. So here's my feed. This sits at servicebus.windows.net/services/clemensv5. That's my account that I use for these demos. And the only thing you're seeing there is a GUID. Ignore that. It's not there. It's an artifact. It's a bug. So this should not be showing. It is. I'm sorry. So this is basically just this is a sign that the naming system knows me, and we shouldn't be showing this, but we do, and I apologize. So what I'm doing now is I'm actually taking this app. Let me just verify that I have the right one, and I'm going to go and start a set of services that are listening and publishing themselves into the registry. And the subtree is called Registry New York, Paris, London, Singapore, and then I have in Sydney, I actually have two endpoints. And I'm starting them from one single application. In reality, I could be starting all of those from separate machines that live in completely different places. For instance, in New York or Paris or London. That's sort of why I named them that way. So those services are now listening. In the public registry, I now see them listed with their names, and when I go in Sydney, you actually see those two services showing up. So it's a hierarchical discovery mechanism that we can use for this. You can opt in or out of publishing those things. So what I did in my program when I opened this is I have a service registry settings behavior that I'm applying to all the endpoints that I'm opening, and I'm saying the discovery type for this endpoint is public. And when I make that public, the endpoint shows up in the registry, otherwise it doesn't. So I'm going to close this, and we'll observe when I start the next sample that there's a little bit of latency to clean up the entire tree. That takes about 2 to 3 minutes, and that's just because of our replication infrastructure needs to get rid of the intermediate nodes, and we're still looking to accelerate that. But once you close them, those endpoints are gone, and you basically just see phantoms of them for about 2 minutes. So let's look at another interesting example, and that's registry publish. And registry publish, I go and get myself a token from the access control service, because I need to have an access token, so that's up here. So I'm just doing a REST request against the access control service, and then I'm creating a base URI in my namespace, Clemens v5, and then I'm going to create a branch and a leaf, and I'm going to register an external address there, and then we go to publish endpoint address. And what you see is that this is an Atom pub call. I'm creating a new item. I'm sticking a WS addressing endpoint reference into it. I'm adding the identity token, so I'm get authenticated. And so this is just an Atom pub call to push an external item into that service registry. So when I run this, we will quickly see that when I go here, there's a branch. There's an external place because I now set the friendly name. And when I go to the internet options and go to content and go to settings and turn off the feed reading view, and it actually listens to me. There we go. You see that I just published an endpoint reference, an external endpoint reference into that system. So what you can now do is you can take just a normal GET request. You can take a syndication feed, you read that into it, you go to the extensions of the syndication item, you can read out the endpoint reference, and then you can stick that endpoint reference into WCF, and it can create an endpoint from that. So a very simple mechanism to register services externally. Caveat for this CTP, the lifetime of those entries is very short. You have to renew them, and renewing them means you basically just put them again and again and again. We're going to make them sticky, but since we don't have a policy checker on this yet, I don't want this to be spammed. So it's a great thing for experimentation. It's not a good way to do link spamming. And that's something we're going to work on. So, where's my clicky? That was the service registry. So you'll see that there's an endpoint reference, that we can put an endpoint reference into that feed. Now, what's a little different from the Atom pub protocol, Atom pub goes and assumes that there is a feed and items, and then probably a feed and items sort of nested. We have a different structure. We have feed, 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 feed. So you post an entry with putting an item into a structure. All names are assumed to be existing already, so there's no post. So you basically just put to an arbitrary place in the structure, and then when you retrieve that back, you actually get a feed. You don't get an item. So that's because we have an infinitely nested structure of feeds. That's how we got to handle it. Let's get to the beefy portion, the messaging fabric. The primary programming model for the messaging system is WCF. And I'm going to talk about alternate programming models, including Java, tomorrow in my talk at 10:15 over in one of these sides, 408. But this is the primary programming model that we have for WCF. If you're familiar with the WCF programming model, you will be instantly familiar with this programming model. If you know the basic HTTP binding, there's a basic HTTP relay binding. There's a web HTTP relay binding, WHTTP relay binding. So all of those bindings that you're familiar with, the mainstream bindings, are all there. Two extra ones. There's a net one-way relay binding, which is for one-way traffic, and there's a net event relay binding, which is for multicast distribution. Most of those are really a mirror of the other ones, also in functionality. What happens if you use the basic HTTP relay binding? You open up a service on your local machine. And what usually happens with the basic HTTP binding is you create a name pipe connection to HTTP sys. You tell HTTP sys, hey, whenever something comes up on this part of the local namespace, send me that request, and that's the way you're getting it. What we're doing is we're cutting that connection, and we're making that connection work with the cloud. So instead of opening up a relationship with HTTP sys, you're opening up a relationship with our cloud listener. So you send an HTTP request up there, and that HTTP request gets routed down to you. We're going to see that all in pictures and how that all works. So we support SOAP 1.1, SOAP 1.2, and none as envelope types, which means we can support REST. We relay plain HTTP requests. We support all W* end-to-end security scenarios. We encourage you to go and encrypt your data. I don't want to see it. Use message security, wrap it all up. I don't want to see it. I don't really need to see any part of it. Transport and sign it all, because you want to make sure that we can't tamper with it. We're not looking at it, we're not tampering with it, and you can prove that to yourself by enabling message security. There's transport level message path protection, which means by default, all listening connections are using SSL, and the sender can choose, and you can enforce by policy to make them use SSL on the socket connections as well as on the HTTP connections. We support reliable messaging, we support streaming, we support the full WCF extensibility model. I'm going to show tomorrow XML RPC through the service bus and blogging through it. The web program model is supported metadata exchange. Not supported, atomic transaction flow. We don't support atomic transaction flow. Two good reasons for it. One, it's not a good idea. Second, if you think it's a good idea, I'll give you that. But in a cloud scenario, you need to have a boss that's sort of sitting up here, and that the DTCs who are sitting locally can actually see, because they need to have a communication path, and we don't have that boss yet. I'm not saying that we will. I'm also not saying that we won't. There may be. But I think we have to do some work on the protocol front to enable more scenarios than just atomic transaction before that's something we can do. Protocol level transport authentication doesn't work. You can't do RFC 2617 auth against our endpoints, because that only works hop to hop. And we don't know what that means. We're not directly supporting it. We're not stopping you from doing that in the pure HTTP mode, because we give you all the headers. We're just ignoring it. Instead, we give you token-based authentication, and I'm going to talk about how that works. The web scripting behavior, AJAX, the JavaScript proxy, doesn't work. There's a bug in WCF that basically always assumes that it's plain HTTP, and that's something we can't work around. So in one of the next milestones, we either have to have WCF fix it, or we need to go and steal the code. And then with the direct TCP modes that I'm going to talk about, there's some constraints with RM and W star security. I'm going to explain why that's so. So the bar on the side of this shall say the unsupported things are really few. The supported things are quite a bit. The not supported stuff got a lot of airtime on this slide, so I just want to make it visible here. Okay, let's dive. Got to do it somehow. So let's dive into this. The net one-way relay binding is our most fundamental binding, and actually all connection modes use this for coordination. You'll see that. So what happens? The receiver means a service is opening up a connection. It wants to listen for messages. Now, keep in mind, this may be sitting on a laptop connected with some not so good connection to the internet. So it now wants to start listening for messages. What it does is it opens an outbound bidirectional socket into the cloud and registers there. It subscribes. The subscription, if that's flowing a little bit along with it, that's actually making that the registration visible in the service registry. So that's what we've seen. So we create this outbound socket, and then it goes to TCP SSL port 828. At this point, we require outbound port 828 to be open, but you don't have to open any inbound port to get that traffic. So yes, in very restricted corporate environments, that likely won't get you out. There is a very aggressive, very evil mode that I'm going to talk about tomorrow that will get you out. That evil part is going to it's come tomorrow. Then the client does a TCP SSL connection, just a one-way TCP.NET connection to another node in the fabric. Now, this is important to note. The backend naming and routing fabric is the system that we run, and then we have the front-end nodes, and we have very many of them. So here's a scaling puzzle, right? A client gets balanced to one node. The server is balanced to another node, so they're sitting far apart from each other. What do we do with those one-way messages? Well, you send a message up. That message gets routed aided by the naming fabric, and then gets routed down to the right node, and that's the way it gets to the receiver. That's the simplest path. That's one way. So there's a socket connection outbound that we keep alive and we reestablish if needed. And you have a name in the cloud-based registry. Messages can be sent to that, and we route that down your socket, and you're getting it. So let's look at this. Now I'm taking a pretty remarkable risk for even my sessions. My network connection is this. T-Mobile Edge, not 3G, T-Mobile Edge, just connected, my private data plan. Not that Microsoft wouldn't pay for it, but I decided to do that demo that way. So I'm going to start this. And this may take a little while because it's Edge. And I'm hoping that it will. Well, what it does now, it goes and acquires a token. And now it's establishing that connection up into the sky. And while that happens, let me go and set up the other thing. Let's see whether that works. And I'm setting up the client here. We have something. Press enter to exit. That's not a bad sign. So if you will observe, well, I can't turn that around really. Wireless is off. There's no network cable in here. This is the truth. Service, isolated from everything else. Shall I call witnesses? Okay. I'm running the client. Client sends messages. Client side, just sent messages. That's pretty amazing, isn't it? Imagine what that means. Imagine what I just gave you. Any machine, as long as the circumstances play along, and this will be true on the majority of small business and home networks, that outbound ports are okay. I just gave you a way to communicate into them. I just gave you a way to communicate and give you that connectivity. It's pretty astonishing. When I saw this first, and see, I didn't invent all these things. Dennis Pilarinos and John Shushak and David Wartendijk should get all the praise for coming up with those ideas in the first place. And I just inherited them. It's a pretty cool thing when I saw this first, and I'm just incredibly proud to be able to carry that flag forward, working with them. The next binding is the net event relay binding. Now, the net event relay binding is kind of the same, except it allows two receivers. That's PubSub. It's not really PubSub, it's a topic. You go and you publish an event out to servicebus.windows.net, to whatever solution, to whatever endpoint you want. So you start receiving on it. There doesn't need to be symmetry. You can start sending events to an endpoint, and that endpoint doesn't need to exist. You can start listening on an endpoint, and any number of listeners can start listening on that endpoint. And we distribute the messages. So the sender sends a message that gets routed to that name and then gets distributed down to all the listeners. That's eventing and multicast for you. We have a little application, and by the way, all the things that I'm showing you here are based on the SDK. So you have all those things at hand. I've just put them into one solution. Here's what we have as the multicast sample. And the multicast sample that I have here, I can go and start a chat session. Oops. Now you're catching me at some let's try this. You know what? I got to apologize for that one. We're going to see how we do on time, and I'm going to do that at the end of the talk because I don't want to stop you from seeing the content. So what you will see, if this works, we're going to see whether I can recover it at the end. I'm sorry. This worked. Well, the real reason here is I know how to get this to work, but I have to do this offline because now I need to put my password in, and I don't want to show you my password. So let's postpone this. We're going to get back to it. We're going to do that during Q&A time. Sorry. The NetTCP relay binding, so that was one way that was eventing. The NetTCP relay binding is the binding you should use for everything unless you have got good reason for do anything else. Because it is going to give you the highest throughput. It's the best thing for everything. The NetTCP relay binding gives you something that's quite interesting. It starts out like Net one way. We punch a hole up into the sky, and we register into the system. And the sender now goes and is load balanced into any of the front-end nodes. The front-end node, yes, this is PowerPoint. You can do it with that. Buy it. It's great. You can go and the sender then starts sending messages to that endpoint. It basically just opens up connection and starts sending. When it does so, it creates a connection, a socket connection to one of those endpoints and hits a socket-socket forwarder. That socket-socket forwarder then says, hey, to the receiver, I have someone for you who wants to connect to you. So what we do is we send a message out, a control message, out to the name that was registered on. We sent that message to the receiver, and what the receiver does now is it connects up to that particular node, and those two nodes get connected. From this point on, it's a pure socket connection. You can do streaming, you can do video, you can do whatever you want over that connection. Here's how that looks. We have a simple, and here at this point I'm going to show you the code. So we have a simple service, because I want to go through several, running all those things is interesting, but I also want to show you the programming experience a little bit. So we have a program. We collect the solution name here, and we create a URI, and the URI is composed of your solution name plus the so this is the host name, servicebus.windows.net. You can get that host name out of the service bus environment default relay host name. Then your solution name is always at the root. So we're collecting that from the keyboard. And then we just create a service host and open that service host. And of course, it needs to have information for what it should open. And the way it does that is by referring to the application configuration file. And what the application configuration file does is it simply has a NetTCP relay binding, and that NetTCP relay binding just works and looks like the normal NetTCP binding. So with that, you just open up those endpoints, and they'll just work. One of the interesting things here is all the demos look really alike. Therefore, I'm not going to run all of them, mostly because it's really awfully hard to demo TCP/IP. So I'm trying, with every sample, I want to just walk you through different aspects of the stack. So, but I'm still going to run some. But so that's the way you go and just configure the binding. We go and have a service. We have an endpoint. We go and refer to the NetTCP relay binding, the default configuration here. So this is normal standard WCF. So the learning curve is very low. and instead of listening locally, you basically start listening in the cloud. To authenticate with the relay, we have an endpoint behavior that we're referencing here. And this one is for card space. We support card space, we support username and password, we support certificates, and we support federation. And the one thing that we usually use in the samples is either card space or username and password, and some of them use certificates. And the way you do this is you go in the portal to your credentials management, and this is where you can register your card space card, and this is where you can also register your certificate, and you can then use that to register. What I've done here for the demos, because I'm pretty protective of my password, as you could just see, and what I didn't do in that demo, just me stupid, is I didn't put that behavior configuration with the demo credentials in there, and that's why it's still asking me. So you take those behaviors, you take one of those behaviors, one of the configuration settings of that transport client endpoint behavior, and then stick that into the endpoint. And this is how you go and authenticate with the system. I'm going to have a graphic about that a little later. The NetTCP relay binding hybrid mode is another interesting one. The hybrid mode, also referred to as direct mode, even though we don't have a pure direct mode right now, is doing a very interesting dance with with network address installation. So this is the status of the system when it is already in relayed mode. So this is a NetTCP connection as we just saw it, right? There's a socket forwarder sits over there, and we have established that connection. Now what we want to do is we want to create a direct socket between the sender and the receiver, even though they're both behind firewalls and even though they're both behind NATs. I repeat that. We're going to create a direct socket connection between the sender and the receiver, even though they're behind firewalls and even though they're behind NATs. Both parties start, as the connection goes up, start probing and send messages up to the relay. They do so on dedicated ports. With the probing, they establish information about each other. I'm going to go into detail on how that really works tomorrow. They get information about each other, and they use a prediction algorithm to see what port is going to be open on the NAT when the next connection comes in. So there's a little bit of a gamble here, but with that, we're actually able to go and create that NAT traversal connection. If you use Messenger and you use the send me a file feature of Messenger, you notice that that is going slow, and then sometimes it's going fast. They're using the same trick. So what happens in this probing algorithm is we send two messages from both sides. Boop, boop. Those two messages are looked on by the relay, and it sees, oh, this is coming from IP address X. That's got to be the external side of the NAT device, and it's using port N. There comes the second one, and this is milliseconds apart. This is using N+1. That's kind of interesting. Next one comes up, different IP address. This is M. The second one comes in, M+1, M+2. That's kind of interesting. And then there's a lottery game, a gamble, say that the next one may be N+2, and the next one here may be N+4. And we just let the other parties know, and they just give it a shot. 80% of the time, we're right. The interesting thing with that hybrid mode is it will try. If it can't snap that socket, it will use it. Otherwise, it's going to stay relayed. So you can start pumping that DVD with your own photos over that connection, and as we upgrade, we're going to upgrade the stream correct by the byte to the direct connection, so you're not going to lose anything. So if you're clapping for the theory, let's see whether we can actually get that to work here. So here I am in an unknown network, and I got it to work in the hotel. let's see where we can get it to work here. So we got a service I'm going to run that's hopefully not going to prompt me for any credentials. That looks good. So now it's listening at service bus.windows.net services Clemens v5 net TCP hybrid demo. And the client will now open a channel to it. Ooh. Oh, did I? Why did you let me do that? It's funny how people sit there, it's going to fail, it's going to fail. So see, the messages are going 470. It's waiting a while. It's doing its dance. It may fail. Send 1. Send 321. So what it's doing while it's thinking, since we're doing that all on one machine, now it's probing look at that.
Right. Wow.
Got it upgraded. So what happened now here is it just keeps sending messages. It does that send. In a second thread on both machines, it goes and starts doing that negotiation dance. And so it went up to 1,400 messages per second. The reason why that happens is because it now snapped the direct socket on my machine. So we're doing the NAT upgrade in 2 ways. We do NAT upgrade first between machines, between networks. And if we sense that it's on the local machine or on the same subnet, we just forget about the whole NAT stuff altogether, and we snap the sockets directly inside our network. But you just saw the effects of it. We send 300 little messages, 400 little messages per second over the cloud system, which isn't shabby. But then once I upgrade, I send 1,400. So that's that direct upgrade mode. So you can start out relayed, and you can go and upgrade. And if you do higher transfers, you get higher transfer rates because you don't pay the latency, depending on where you are. You don't pay the latency of going into the Microsoft data centers. And that's a mode that I believe is going to be very, very interesting for very many applications. So let me just clean the house a little bit, including this puppy. And get on. So that was the hybrid NetTCP relay binding. This is one of our flagship bindings, and we're pretty proud of it. Making this work is, as said, a little bit of a gamble. Our success rates are surprisingly high, but if it fails to upgrade at some point, you still have the relay connection. A thing that we're going to give you in addition to this, in one of the next milestones, is you can basically constrain it completely to direct. So right now we only do the hybrid mode. There is a direct mode that's in the API that is exactly identical to hybrid right now, but it's going to be different from it once we have that feature enabled, which basically means we're going to suspend all sends until we have the socket connection established. If we can't establish that socket connection within a specified timeout, we're just going to fault the channel. If you're worried about sending any data through our cloud. WS Basic Web HTTP relay binding. That is what you saw what Don and Chris used. Don and Chris wrote this little service. What did they call it? The process monitor or something like this. And then Notepad through the service bus. And in reality, the way they built this, if you had known enough details about the demo, you could have shut down their entire system at that point in time. I'm telling you now. But basically, it literally would have taken a HTTP delete to any of the services that were showing up in their list, including unimportant things like service host, WinLogon, all those. Yeah, it was the entire purpose of the presentation for them to get hacked. It didn't happen. See there. So the receiver, same thing, goes and registers. Sender gets load balance, same dance that we had. Now we're hitting this HTTP socket forwarder. We're doing that by, we differentiate between the protocols on the client side, and this is why we need separate ports. So this is being hit by HTTP or HTTPS requests. So you basically come on with a request. We do the same dance as we do for NetTCP. We send a control message. That control message goes down to the receiver and says, hey, there's someone waiting for you with an HTTP request. We go and do a rendezvous connection up to that particular service. That's what your client does. And then that request actually goes through. That request goes through, and then you have an HTTP request going on. Same thing. It's just not. It's not a one-on-one socket connection, but it's an HTTP two-socket connection. We pool those connections to your receiver on the server side, and you also pool them on the receiver side. One of the things that we're going to do, you remember where I said the solution in the namespace goes first in the future milestone, where it goes into the domain name. This is what we're going to do to constrain the size of each individual pod that's going to host requests, because that actually has implications on the scalability and the load we're putting on your services. That's why we're saying the NetTCP binding is something that you should use in doubt, and then use the HTTP binding if you need the interoperability, because we have a lot of machines over there. And if we have a lot of machines and the load balancing is actually fair, we can't use all the pooled connections. So you got to make that a little more narrow so you can actually leverage the pooled connections to your service. So that's scalability work that we're doing to make them more efficient. So you'll see that the net effect of that, what you're seeing, is you see a little more memory load on your services that you're running, and the latency is higher because you need to reestablish connections more often than a NetTCP. So I'm going to show you those things. What I'm going to do here is I have a little web HTTP service. That's called the simple share sample, and that's also opening up in my branch. I should probably turn that back into the mode that where we can actually see something. So here's my simple share service that just opened. Again, this is accessible from the public internet, so if you have your computer open, feel free. You can literally do that right now. It's unauthenticated and everything. It hits a share on my computer, and we can go into videos, and we can go into shopping holiday WMV. Now we're now actually establishing that connection just as I told you. It's taking a little while, but it's also because it needs to go and invoke our good friend Windows Media Player, which now got the URL. Windows Media Player is now going to that URL all by itself, and it's streaming slowly but surely that video through the relay from my machine onto my machine, which is not a big trick, but I could hit that from any machine, so if you were hitting that URL, you can see the video right now. Also, a pretty amazing trick. That's REST for you. You can clap. Oh, the W is HTTP relay binding. W is HTTP relay binding. It's not as exciting as one of those additional samples. So again, I'm going to show you the code here. The program is like all the other programs, except that it's using the HTTP format. It can also use HTTPS if you turn on transport security. So we're supporting HTTPS on the server. We're supporting HTTPS from the client. The client can always choose between HTTP and HTTPS. We treat them completely alike. If you're listening to HTTP and you send using HTTP, you have a secure channel on the back. The client can choose between them. If the server chooses to listen with transport security enabled and with HTTPS, the client must use HTTPS. So the client has a choice if it's in unsecured mode. The client doesn't have a choice if it's in secured mode. And then the way to enable this, actually, is you go and use the WSHTTP relay binary. In this particular case here, I have reliable session enabled, and I'm using just a normal Windows security mode. What that means is that I can actually use Windows credentials for the end-to-end security, which is kind of funny. What you usually would do, so with cached credentials that you have on your machine, with cached domain credentials you have in your machine, you can actually go and use a service that sits in your corporate perimeter that's AD integrated. Usually you wouldn't do that way. You would usually use our federation support that's in the access control service to actually secure that connection and use it that way. But you can use security, you can use transport security, you can use message security, and you can use all the options that are there. So let's go and hop on to the next thing. And that's talking about the access control integration. It's actually a good segue into this, how this works. So further demos are going to be in a slide. I think I threw a lot of code at you already. Access control model for the listener. How does that work? The receiver goes to the access control service, and we've seen a little bit of that in the service registry sample. So this is the place where that really gets explicit. Let me go and flip back to that so you can see it. This is the REST version of this. So let's go and look at the registry publish service again. So what we do here is we go to access control.windows.net/issue token for Clemens v5, and password is, I'm not going to show you. So we go there to get a token issued. This is the REST path. What you're getting out of this in the REST path is you get a little base64 encoded reference. That references a token that's kept by the access control server. It's issued to you, but it's put into storage, into volatile storage actually. They're giving you the token, and you come with that token back to us, and we're looking up that token for you so that it's small. In reality, so this is the most visible way of showing you this. In reality, what we do with all the other things, and this is what this transport client credentials behavior is for, the thing that I showed you in config, is that is controlling how our infrastructure, the token providers that are part of the programming infrastructure, how they go and acquire that token. So they go and, so the receiver first goes and acquires that access token, and it asks for a particular claim. And the claim is the listen permission on the service bus. So when you go into the access control portal, and Justin Smith is going to talk about that in his talk, when you go to the access control portal, you will see that you can define rules for listen and send permissions. So you can allow other people, you can allow identities who come from other federated systems, somewhere in some AD member of a particular group, they come in with that credential, and they can get the listen or send permission based on a set of rules that you can define in the access control portal or also programmatically. So we first acquire that token. We do so by the REST path by providing username, password. We have a number of credentials you can use with the W's trust path that's sort of baked into the program model, so you get that token. That if you, with your identity, are entitled to that claim, so you can get that listen permission, the token is going to be issued to you. If not, it's going to tell you, I don't know who you are, or sorry, you can't do that. But if you get that token is then issued for the service bus relay. You can look at that token. So if you were doing interop work, you could get that token, you can look at it, and what you're going to see is it's a token, and it's going to expire then. That's all you get to see because the rest is encrypted and signed and issued to the service bus. So you can't even look at the claims that are there because they're none of your business. That is then, and this is true for even if you use the access control service directly for your systems, if any client acquires a token and acquires a set of claims, that's none of their business what actually is in there because you don't want them to tamper with it. The access control service says, yes, this is the truth. And therefore, nobody can tamper with the truth. Therefore, it needs to be passed as is without any chance of modification down to the service bus relay service. The service bus relay service gets that token header in a message or when the connection is established, depending on the connection mode, and we evaluate that token. And what we do is we check, is this a token that's issued by the access control system, and does it have the right claim? If it does so, we let you open that connection. That's the listener part of it. So if you look at the access control portal, you'll see an action, and that action is called listen. This is what it's for. It's for allowing you to start listening on the relay. This is really important because it controls your namespace. It governs access to your namespace. You can open that up to everybody if you're crazy, but you can allow, there's an everyone keyword that you can use instead of the user, and that will allow everybody in. You just shouldn't use it, shouldn't do that because we have quotas on the number of connections, and which means that we can dial you down. We're going to see it. We don't see what you send, but we certainly know what the number of connections that you're creating because you're using resources. The sender goes up to the access control system, also acquires a token, and then sends it along with a request where it's evaluated, and then we're picking that out, and we're taking that out, and we send the message along without it. Because it's not the receiver's business what token you brought to get through the relay. The integration of this with end-to-end security is the composition with end-to-end security is, before I get to the summary, I should tell you that, is that we are reserving the W security headers for exclusive use for your application. So if you want to do any end-to-end security in any shape, way, or form, with or without our model, you can go ahead and do that. You can sign all the headers. You can go and encrypt the message content. We're not looking at it. The only thing we look at is where does that message come from, where it's sent to. So we need to look into the to header, which ought not to be encrypted in any case, but it can be signed. And that token header, which we need to be able to see, and that the token in that header is always encrypted. You can also construct that, and we're going to put more protocol documentation out over the upcoming few months. I'm going to give you a little more detail about that, about how you can construct that in an interoperable fashion. I'm going to show you some Java code on how to do that integration. So the relay access control model is very easy. You can go and provide send and listen access on a per URI basis for your entire namespace by creating access control rules, and you centrally manage them. A sender can opt out of this scheme. This is what we just saw. My application that I just ran, the Get My Video little app, that application is an app. Did I stop that, by the way? No, I didn't. So I'm going to spoil the party. That application opted out of this mechanism. The way how we opt out of this mechanism is always the same. Let me find it. We have that here. And on the security binding element, of the web HTTP relay binding or security setting, configuration settings, there's a relay client authentication type. That is a difference to the standard WCF programming model. There's also a respective knob on the object model for it. This has two permitted values. The standard value is relay access token. That's the policy, the default policy, which requires, as per the listener, all clients to bring a token. If you set that to none, as in this case, the listener takes responsibility for security and basically says, I don't want integration into the access control system for all the clients. The listener always needs to acquire and bring that token, so it needs to have permissions as per the access control system, but it can waive that requirement for the clients. The interesting side effect of that is, if you turn this on, if you turn that off, and you go and do a MEX request, so you acquire metadata for the endpoint through the relay, and you get that back, and you run this to service util, and you're exposing this through, let's say, the WHTTP relay binding, you will find that the output, the generated binding on your site on service util, is the web HTTP binding. So if you are willing to take the risk of getting unwashed traffic, of getting traffic that is not guarded by our access control system, but if you say, I'm fine with doing my own access control, as I've done before, you can totally do this. And then it is sufficient to use the standard WCF 3.5 programming model against those endpoints. If you are turning this on, you need to have our programming model, because our programming model, our extensions to WCF, know how to generate and acquire that respective token. So all the access control to the system is managed in the access control service, and you have full control over your namespace. If you want everybody to listen, if you want everybody to send, you can do that. It will hit your quotas. Our quotas are currently, I believe, at 10 open listeners concurrently per solution. And that's something we basically just do to guard our system as we ramp up. We can dial them up as we observe the system. If you would open it up to the general public, your quota will be hit pretty much instantly. So I would recommend that you don't do that. But you can go and start playing and have, if you have multiple solution accounts, amongst your friends here, you can start granting other people permission. You can certainly go and look at all the federation options that we have and start federating with identity providers that you maybe have, and then let everybody from LiveID into it. So that we have samples that explain how to do federation with LiveID. I would also encourage you to look at their blogs from Justin Smith and me. And you're going to find most of those linked from the Azure Developer Portal, so we don't have to swamp you with all the URIs. You're going to find all that information over the course of the next weeks. We've been very busy getting this stuff together, so now we actually can go and take a little rest and get to writing and explain more about those things as they work. So the best documentation that we have, I think, reasonable good documentation in the SDK, which I encourage you to read, and the security part in particular. So some notes on security. We encourage you to hide your payloads, as I already said. Do that. Use message security whenever you can. Transport security, all the SSL channels that we're creating this way with the relay connection, they terminate in the service bus. So yes, your data travels in the clear for a moment. In the clear, meaning inside of our service bus fabric. So yes, we, evil Microsoft, could possibly look at your messages. I don't know how to build a system which would actually be able to look at your messages, because I don't know how to handle all that much data. So I'm too stupid to look into your messages. But if you use WSecurity, you're perfectly clear. You can prove to yourself that we can't look at them. The socket connections, if you use this SSL relay mode, are relayed on the machine in a tight loop of 2 threads. And they're not, so your bits are not getting out of that loop of 2 threads. the one-way fabric, where one-way messages might travel in the clear, is completely isolated from the internet. What do we look at? We look at SOAP action, we look at WS2, we look at the HTTP method, and we look at the URI, and we look at the access tokens, and that's it. So we don't touch the payload. For us, touching the payload is actually very expensive because we assume that everything is streaming. So you start sending a message, and as that message is still coming in, we're already sending it out. So for us to actually peek into it would be horrendously expensive. So we don't do that. So summary. I think this is pretty cool tech. I think this is enabling a lot of scenarios, and I encourage you to play with it and think about what it can do. Now, one important thing when we think about security, what I'm not doing here, or what we're not doing here, is we're not punching holes in your firewalls. We're explicitly not doing this. We're taking mechanisms that are available, and we're allowing you to selectively expose endpoints on the internet at your choosing, and we're creating a demilitarized zone in the sky that you can leverage. That's the way to look at it. I'm not punching holes in any firewalls. We're not doing anything illegal by any standards. We give you all the port numbers. You can open them. You can close them. So if you don't like what we're doing, you can defend against it. In my session tomorrow, I'm going to show you a way how we make that a tiny little bit difficult to defend against for two particular modes, where we can actually do HTTP polling for one-way and relay. And that's also what the Java samples that we have and the Ruby samples that we have, and the Ruby SDK and the Java SDK that are being developed by our interoperability team with their partners that's what they're using. So I'm going to talk about more protocol details. I'm going to talk about cross-platform support and a look under the hood. That's all happening tomorrow at 10:15. And with that, I thank you for your attention. Fill out your evals. That's very important for us because we get paid based on that. And with that, I have 5 more minutes for questions, I believe. Thank you. Any questions at the microphone? Everybody leaving? Happy to be gone? Yes.
So it sounds like the clients have to be connected to receive your messages, right? So there's no store and forward capability.
Yeah, so thank you. Thank you for that question. There's no store and forward capability. That's the question. At this point, there is no explicit store and forward capability. It's one of the things that we're going to do next. So everybody's asking for it. Do you guys have a queue? I say no. We're working on it, and we're actually working on it.
Oh, sorry.
So that means we have to build our own pub sub capability in the sky.
Well, you currently have eventing, which is volatile pub sub, and so there's a topic-based eventing system built there, where yes, you have by virtue of the URI, you already have a pub sub system. There's just no pub sub in the sense that they can be temporally disconnected. So will there be a queue? Yes, and once we have a queue, that's covering that topic.
Oh, no problem. Yeah. The machine that your receiver is running on, it was not necessary to open any inbound ports on that machine.
No
How is the notification done from the service bus then? How is the receiver notified?
As I explained to you, it creates an outbound connection up to the system. We maintain that outbound connection. That outbound connection has a name in the service bus fabric. We sent that message over there. We route it to that machine that owns the socket, and it sends it down that socket.
Even in the case of HTTP relay?
Yes, the HTTP.
That's what I was.
The relay HTTP mode is the listener is using a socket, the sender is using HTTP. I'm going to explain the HTTP path, the HTTP listening path tomorrow.
Okay. The receiver's using a bidirectional socket in that
Yes.
case. Okay. Thank you.
So it seems like, at least currently, most of your scenarios are, it's really like a service router. So are you, at least for the foreseeable future, you'd envision like just kind of exposing services from your own ESB inside the firewall out, not really acting like a full ESB in the cloud?
You mean hosting? So composes with workflow, with our workflow capability, and you're getting closer to that. So workflow is there for service orchestration. So it can do right now. It can do content-based routing. In a future milestone, it's going to be able to do transformations as well. So we're getting closer to that capability. So we're architecturally separating those things. So so this is the messaging fabric, and what we're additionally doing is creating the orchestration fabric, which is workflow.
So you plan on exposing more, but at least for the foreseeable future, it's really a lot of routing and not like transformation. When would you expect things like that?
In one of the next milestones, so half a year at most.
Cool. Thanks.
And that will be in workflow, not in the messaging fabric. That's in workflow. Okay, one more.
How are Silverlight 2 clients going to be able to talk to these services?
Through the HTTP protocol.
Is there a cross-domain policy on the service bus?
We're putting one in.
Okay, thanks.
So that's great question. I knew about this. We got it. We're looking into how to do that right with the Silverlight team. So there's a little bit of trickery that we need to do. We're going to do a refresh of this build in the data center in probably a month or so, and that's one of the things that I want to get in.
Great.
Thank you very much.